Hi, welcome to this video on linear programming duality. In this video, we're going to be discussing the equivalence of Farkas lemma and strong duality. So we've already seen that Farkas lemma is implied by strong duality, but in this video, we're going to be proving the reverse direction, that is to show that they are actually equivalent to each other. So we proved Farkas lemma initially by using strong duality. So it's worth noting that we could have instead started with Farkas lemma and then used that to prove strong duality initially. So instead of proving strong duality via the simplex algorithm as we did, we could have started with Farkas lemma. That would have required us to come up with a new proof from scratch for Farkas lemma, and that would have required us to venture out into more general polyhedral math and linear inequalities and things, and that's fine, but this way we were able to keep everything at least contained within the tiny world of basic linear programming. The simplex algorithm certainly falls into that domain. So anyways, it doesn't really matter which order you prove things in because they all end up being equivalent anyways, but this was the route that we chose in this series of videos. So before we prove strong duality, let's just remind ourselves of what Farkas lemma is actually saying. So it says that if we're given the system ax equals b and x non-negative, then exactly one of the following is true. Either one, there exists an x bar such that the constraints are satisfied, so this system is feasible, or two, there exists a y bar such that these constraints are satisfied, and these are what we call a certificate of infeasibility. Well, a y that satisfies these constraints is what we call a certificate of infeasibility, because if such a vector y exists, then it's impossible for condition 1 to have been satisfied. And the reason that that's true, what we proved when we proved this statement, is we said that there was a primal dual pair of linear programs operating in the background, where for the primal, these were the constraints, and we were maximizing the constant objective function 0. And so for the dual, we know by weak duality that its objective function is always going to be at least 0, because it's an upper bound on the primal. And so if this vector y exists, then this condition 2 is saying that y is feasible for the dual. That's what this constraint is, and the objective function value is strictly negative. So in other words, it's strictly less than the value for the objective function of the primal. That's impossible by weak duality unless the primal could not have been satisfied in the first place. So that was the reasoning that we went through at that time, and I'm reminding you of that because now, for this video, we're actually going to use a variant of Farkas lemma. It's still Farkas lemma, but it's just dressed differently now. So instead of our system being ax equals b and x non-negative, take a look down here, we're going to be given the system ax less than or equal to b. Now what Farkas lemma would be saying is that, again, we're just going to take a primal with objective function constant 0, and the constraints are all less than or equal to constraints. So this is the version that we're going to use because it'll be easier for us to prove strong duality with this format. And here, so what should the same logic do? Well, we should take a primal dual pair of linear programs, and either condition 1, it will be that the primal is feasible, so these constraints will be satisfied, or 2, there exists a y bar such that the dual constraints will be satisfied, and these are the dual constraints, and b transpose y bar is strictly less than 0, and again 0 would be the objective function value for the primal. So it's impossible for condition 2 to happen if the primal is feasible, so it must be that if condition 2 holds, the primal is infeasible, or in other words, this system right here is infeasible. Anyway, so it's the exact same logic, but instead the constraints are written like this, and this is the format that we'll use in this video. Okay, so now let's actually get into the proof of proving strong duality. So we're going to be given a primal dual pair of linear programs, so the primal on the left and the dual on the right, and so you can see that the primal will be given in this very general way, the most general way, where all the constraints are less than or equal to. And just so that some notation doesn't get totally confused, I renamed the matrix to be M rather than A, but whatever, it doesn't matter whether it's M or A, it's just notation. Anyways, what's strong duality going to say? Strong duality, it says that if both the primal and the dual are feasible, then that means that the optimal values are equal. So the optimal value of the primal is equal to the optimal value of the dual. Okay, and so this is what we want to prove in this video. So I guess we can just box this off real quick, and we'll get on to proving it. So our proof will be like this. What we're going to do is, well, let's assume the hypotheses, first of all. So assume the primal and the dual are feasible. And we already have weak duality. Weak duality is going to tell us that the optimal value of the primal is at most the optimal value of the dual. So what we're going to do is, let's assume for contradiction that actually they are not equal. So assume for contradiction that that the optimal value of the primal is strictly less than the optimal value of the dual. And we're going to derive a contradiction from here. And that's going to show us that actually this bound can't be strict, so in fact they have to be equal to each other, and that'll prove strong duality. For some notation, let's just denote the optimal value of the dual to be gamma. So gamma is defined to be this number here, the optimal value of the dual. And so what we're saying by saying that the optimal value of the primal is strictly less than gamma is we're saying that there cannot, so therefore there cannot exist a vector x bar such that m x bar is less than or equal to b and C transpose x bar is at least gamma. Because if x bar is feasible for the primal, so it satisfies these constraints, then C transpose x bar, the objective function value, can't be any more than gamma. It must be strictly less. So this would be impossible. So this x bar does not exist. This constraint, the second one, so we can rewrite the C transpose x part of it. Well, let's just rewrite all of it. So mx less than or equal to b, and minus C transpose x bar is less than or equal to minus gamma. Is another way we could write that second constraint. So now everything is less than or equal to constraints. And so what we can do is we can write a block matrix to capture all of the constraints given here. So, so this is equivalent with saying there does not exist x bar such that this matrix, which is M followed by the vector minus C transpose times x bar, is less than or equal to the block, which is B minus gamma. So if you just read these constraints across, what we're saying is that mx bar is less than or equal to b, and minus C transpose x bar is less than or equal to minus gamma. So minus gamma, of course, this is just a single number, corresponding to the fact that minus C transpose, this is just a single row. So M is an overall matrix, and then we've attached one more row down at the bottom, which is minus C transpose. Same thing here. B is an overall vector, and we've attached one more component, which is minus gamma. And so, yeah, this overall system of a matrix times x bar being less than or equal to this vector cannot be satisfied. So, since it can't be satisfied, we can use Farkas lemma. And so what's Farkas lemma telling us in this case? This would say that, therefore, there must exist, I was going to call it y bar, but let's call it z bar for the moment. So there must exist a z bar vector such that the transpose of this matrix, so M minus C transpose times z bar is equal to 0. That vector z bar must be non-negative. And finally, for this right-hand side component vector, we'll have B minus gamma transpose times z bar is strictly negative. So this equivalence here is by Farkas lemma. So that's the first time that we're using it. Again, we're using that new variant, that equivalent variant that we introduced, because these are less than or equal to constraints. Well, do you see how this matrix is an overall matrix plus one more row at the bottom, and this vector over here is an overall vector plus one more component at the bottom? So let's do the same formatting with this vector z bar as well. So we're going to write it suggestively like this. So z bar is going to be equal to y bar and then lambda. Okay, and so y bar will be the entire vector except for the last component, and the last component is lambda. And so what we can do is we can just rewrite these constraints then. So what we'll have is once we take the transpose of this matrix, we'll have M transpose and then a column vector, which will be minus C now as a column. So that times the vector y bar lambda equals 0. The next part, this part here, will become y bar lambda non-negative, and then the final part will become b minus gamma transpose times, of course, y bar lambda is strictly negative. So now what can we do with this? Well, let's rewrite it one more time. You see, if we do the multiplication here, we're going to get m transpose y bar minus c times lambda equals 0. The next part will tell us that y bar and lambda are both non-negative, where lambda is, of course, just one component and y bar is the rest of the entire vector, but nonetheless, they're both non-negative. And then finally, the b transpose y bar minus gamma times lambda is negative. With these three conditions, we're going to basically derive a contradiction, because if I just circle these three things real quick, we're going to use them and get this contradiction based on lambda. So see, lambda, there's two situations. Case 1 is that lambda equals 0, and case 2 is that lambda is strictly positive. Lambda can't be negative because, of course, we're assuming that it's non-negative, so either it's exactly 0 or it's positive. And in either case, we're going to get a contradiction. So let's deal with case 1 first. So if we're in case 1, then lambda being equal to 0 simplifies all these constraints here, so we can reduce, and what we'll get is m transpose y bar is equal to 0, y bar is non-negative, and b transpose y bar is strictly negative. Now, it's kind of suggestive that we used the notation y bar here because y was the name of the variable. If we scroll back up to part of close to the top here, y was the variable for the dual variables of this dual linear program. But it's not true that y bar is feasible for this dual, because you see here we have m transpose y equals c, whereas down below what we have is m transpose y bar equals 0. So this y bar isn't feasible unless c equals 0, of course, but it's probably not. So let's just assume it's not feasible. But what these conditions are saying is these are the conditions exactly dealing with Farkas lemma yet again. So let's just scroll back to the top dealing with that Farkas lemma variant. So you see that exactly one of the following is true. So the first condition isn't what we're dealing with. It's the second condition. There exists a y bar such that the matrix transpose times this vector y bar equals 0. It's non-negative, and b transpose y bar is strictly negative. And our vector y bar satisfies these constraints. And so that makes it a certificate of infeasibility for the original system, ax less than or equal to b. Actually, our matrix is called M, not A, but again, whatever. So mx less than or equal to b is infeasible then, because that's what y bar says. It's a certificate of infeasibility. So there does not exist an x bar such that the system is feasible. But you can see here that's ridiculous, because that's mx less than or equal to b is exactly the constraints of the primal, and we started off by assuming that the primal and dual are both feasible. So of course mx less than or equal to b has a feasible solution. So we get a contradiction. So let's just scroll back down. So when we combine these three things together, we get implied by Farkas lemma. So Farkas says that y bar is a certificate of infeasibility. And so that says that there does not exist an x such that mx is less than or equal to b, and that's a contradiction because, of course, there do exist x. There are x's that satisfy mx less than or equal to b because we're assuming it's feasible. So it can't have been the case that lambda was equal to 0, because then you would have found that y bar is a certificate of infeasibility. Now, what if we're in case 2? In case 2, then what's going to happen is that lambda is positive, and now that it's positive, basically we're going to be able to divide. And so let's rewrite these circled constraints, but let's move things to one side. So we'll have M transpose y bar is equal to lambda c. We'll have y bar is non-negative and lambda strictly positive. And then finally, this final constraint will be B transpose y bar is strictly less than gamma lambda. So B transpose y bar is strictly less than gamma lambda. Again, remember, gamma is the optimal value of the dual. What we can do now is divide by lambda for all these parts. So what we're going to have is M transpose times the vector y bar over lambda equals c. And then correspondingly here, let's divide by lambda just for the fun of it, I guess, but you'll see why we're doing it in just a moment. So we'll have y bar divided by lambda is non-negative. And then finally, B transpose y bar over lambda is strictly less than gamma. And okay, so the strict inequality doesn't change direction because the lambda we're dividing by is positive, so this retains its direction. And same thing here, the y bar vector is still non-negative after dividing by a positive value. And then, of course, for equality constraints, it was never a concern. And by the way, I know it kind of looks like a block vector here, but only sort of, because z bar was defined to be y bar followed by the component lambda. That's not what we're saying here. Here, we're just looking at the vector y bar without lambda, and then we're dividing that vector y bar by the number lambda. So we wrote the division kind of sideways here, so it's not confused with a block vector. Okay, but now if we take a look at these constraints, we get another contradiction, because what this is a vector, y bar over lambda, and it's feasible for the dual, because it satisfies M transpose times this vector equals C. It's non-negative, so that makes it feasible. So these two parts together imply that this vector, y bar over lambda, is feasible for the dual. But then here we also have that the objective function is, when you plug it in, you get B transpose times y bar over lambda is some number which is strictly less than gamma. But gamma was supposed to be the optimal value of the dual. And in the dual we're minimizing, so we shouldn't be able to find anything smaller than gamma. And yet we've plugged in y bar over lambda and it's feasible and it's smaller than gamma. So that's a contradiction. So all these facts combined, feasibility plus this fact, mean that we have a contradiction here. So we can put a little squiggly line to indicate contradiction, and that's actually the end of the proof, because in either case, whether lambda was positive or 0, we run into a problem, and so this lambda couldn't ever have existed, but of course it came from the assumptions that we originally had. So therefore, it can't be the case that the optimal value of the primal is strictly less than the optimal value of the dual, and so that implies that the optimal value of the primal is equal to the optimal value of the dual, and that's strong duality. So that concludes the proof of showing that Farkas lemma implies strong duality, and this shows that actually the two statements are equivalent to each other. Now that we've proven the equivalence of Farkas lemma and strong duality, we can actually end on something that's kind of fun. It turns out those are not the only two statements that are equivalent to each other. There's actually this entire class of theorems that are all equivalent to each other, including those two. And so it's kind of Farkas folklore in a sense that some researchers at some point probably knew that some chunk of these theorems were all equivalent, and other researchers probably knew that other theorems from a different chunk of this overall list were equivalent, but probably very few people actually knew at any point, or even now, that all these theorems are all equivalent to each other. And so you might find out through the grapevine that one of your favorite theorems that you use is actually equivalent to Farkas lemma, and you might get surprised by that. So I found this paper online that actually lists about almost 30 theorems that are all equivalent to each other and to strong duality in particular. And so I just picked out a few of the most interesting looking ones, and I thought we could just take a look at them real quick, not to prove them, but just to see what they are. And if you're curious, I'll put the link in the description to that paper where you can read about all the theorems, and they do give some brief proofs of all of them as well. So this first theorem is an example that's talking about separating hyperplanes. So if V1 and V2 are pointed linear polyhedral cones that intersect only at the origin, then you can define a hyperplane by this vector y that satisfies these constraints, which is equivalent with saying that it's a separating hyperplane. So, maybe here's cone 1 and here's cone 2, and then since they're separate, what you can do is you can separate them by a hyperplane, which would be defined by the vector y. Obvious in 2 dimensions, but not quite as much in high dimensions. Anyways, this is equivalent to strong duality. So we can take a look at another example. Here is von Neumann's Minimax theorem. So this is what it says apparently. If you have vectors that whose components sum to 1 and are non-negative, then if you take this matrix product of a vector y and x times this matrix B, and it's just an arbitrary matrix B with real entries, then if your x and y are non-negative and have their components summing to 1, then you can reverse the max and the min. And that's not obvious, but that can be done. Here's another. This is talking about just the feasibility of a system. If q is orthogonal, then I plus q and I minus q define some constraints, and you can always find a positive x that satisfies these constraints with non-negativity. And then finally, here's a theorem that looks a bit more familiar to what we're used to with Farkas lemma. The prime here is supposed to be a transpose. So either A transpose U is positive or B transpose U, either A transpose U is positive and B transpose U is non-negative for some vector U, or AX plus BY is 0 for some non-negative vectors X and Y, but never both. And so that's the thing that sounds similar to us, because you have 2 conditions, exactly one of which holds. So this seems similar in that spirit. So this one seems like it would be a bit more plausible to try and prove using Farkas lemma, and vice versa. But anyways, those are the ones that stuck out to me as being pretty interesting. Again, I'll leave a link in the description if you want to take a look and see more of these equivalent theorems for yourself. So that actually concludes it for this video, and actually for this topic of elementary duality overall. There's, of course, more things that can be said in more advanced notions, but as far as just getting the basics down and all the things that you can't not know regarding duality, we've really hit the major talking points now. So maybe I'll make a video that'll just conclude everything, give a synopsis of what's happened, but that's really it, at least for this initial series. So if you have any thoughts, let me know, and otherwise, thank you very much for watching these videos.